In the previously discussed modules, so far we have looked at simple linear regression models and multiple linear regression model. In both cases, we had a continuous response variable or a continuous dependent variable, which was y, and we had continuous variable for the independent variables or the predictors. In case of simple regression, we had one predictor, and in case of multiple regression, we had multiple predictors. However, there could be another type of regression model which we would like to fit to certain data set where the independent variables or the predictor variables, which we denoted by x, are no longer continuous, but they are categorical. For example, if one of the independent variables that we wish to include in our model is gender, in that case it is categorical because the data is either for male or for female. In such cases, we use a regression model with a special kind of variable, which is dummy variable, which allots a number to the different categories that x has. In this module, we will discuss the introduction of dummy variables in a regression model, and we will see what kind of interpretation we have for the regression coefficients under the dummy variable setup. In the modules so far, we have looked at different regression models where our dependent variable y and the independent variables x or x1, x2, xp in case of multiple regression were all continuous variables. However, there could be a situation where one or more of these regression predictors or independent variables, which are denoted by x's, could be categorical. So, oftentimes in social sciences, variables are qualitative or categorical in nature. For example, if we want to base a study on comparing the different attitudes of male and female, in that cases, the gender used as an independent variable would be categorical. So, when we have a regression setup where the independent variable is categorical in nature, then the estimation of the parameters of model is still straightforward, although the interpretation of the parameters are not the same as they were in case of simple and multiple linear regression. So, what could be the examples of categorical variables? Whether a person voted or did not vote, or the party choice of an individual, or whether the respondent to a questionnaire is male or female, or the religious denomination of an individual. These are variables that are categorical, which means they reflect a quality, they are qualitative. However, they can still be used as predictor variables in a regression model. And when we want to use categorical variables as one of the predictors in a model, we use regression models with dummy variables. So, let us write down a regression equation with two independent variables. The dependent variable here is y. So, we write y hat equals beta naught hat plus beta 1 hat x1 plus beta 2 hat x2. Now, if x1 and x2 are continuous, then the usual interpretation of the estimated parameters would be for a unit change in x1, beta 1 hat is the amount of change in yi hat, keeping x2 fixed, and vice versa for x2. But when the independent variables are categorical, then fitting a regular regression model would not be correct. So, to take care of the situation where categorical variables act as predictors, we use coding categorical variables so that these coded variables can be used as a predictor in the regression model. So, let me introduce you to a dummy variable regression model. Let us suppose that the following is a regression model with the independent variable being a dichotomous variable. By dichotomous variable, we mean a variable which takes two possible values. For example, if we ask a respondent whether they voted or they did not, there are two possible answers to this question. So, the data collected from n individuals on this particular variable would give us a dichotomous type of data for the dichotomous variable. That is, when the variable takes two values, then let us write down the regression model. yi hat equals beta naught hat plus beta 1 hat times d1i, where d equals 1 if the value of the prediction of y is given by beta naught hat plus beta 1 hat times 1, which is equals beta naught hat plus beta 1 hat. So, the estimate of the response is nothing but the sum of our estimated slope and intercept parameters. Again, when d equals 0, the value of the prediction of y is given by beta naught hat plus beta 1 hat times 0, which equals beta naught hat or the estimate of the intercept parameter. So, when we have a dichotomous dummy variable, they give us the difference in intercepts. When d equals 1, we had seen yi hat equals beta naught hat plus beta 1 hat, and in case of d equals 0, y hat equals beta naught hat. So, the difference of these two predictions simply gives us beta 1 hat without the presence of any predictor variable. So, note that since the model does not contain any continuous predictor, there is no slope coefficient. What we have here is beta 1 hat, which is the difference of the two intercept terms from the two models based on the value that the categorical variable d had taken. So, sometimes the categorical variables are included in the model to account for the change in y that is specific to a group or attribute. For example, we have a model where we have the continuous response variable y, and it is regressed on a continuous variable x and a categorical variable y. Suppose let us consider there is a model with a response variable y, and we regress it on two predictor variables, one of which is continuous denoted by x1 and the other denoted by x2 is our categorical variable, which takes the value 1 when the respondent is male and takes the value 0 when the respondent is female. So, after we plug in the values of the continuous variables, for male, since we consider the categorical variable to take value 1, we replace x2 by 1. So, now we have a model which gives us an intercept of beta naught plus beta 2 plus beta 1 times x1. Again, for female, where x2 is 0, then we have a model with intercept beta naught and the slope is beta 1. So, the model looks like beta naught plus beta 1 x1. So, thus we can use these two models to compare the change in y that is specific to gender. We can generalize this for any other categorical variable used for a specific group or a specific attribute. So, now let us see how the inclusion of dummy variable affects a model that contains a continuous predictor. As I had already explained in the example, when we have two variables, one of which is continuous and the other is categorical, consider the model yi hat equals beta naught hat plus beta 1 hat x1i plus beta 2 hat d1i, where beta 1 hat is the coefficient for the continuous variable and beta 2 hat is the coefficient for the dummy variable. The first model, which only contained a dummy variable, only gave us the difference of intercept. We had seen that in one case where categorical variable was 1, the predictor variable was beta naught hat plus beta 1 hat without including any continuous predictor, and when d equals 0, we only had the predictor variable equals beta naught hat. So, thus the change in y actually just gave us the difference of intercept. But when we consider the above model where we also included a continuous predictor variable, then the model will give us difference of intercept, but two lines, regression lines, which are parallel. So, consider the model from the previous slide. When d equals 1, we have the response predicted by beta naught hat plus beta 1 hat x1i plus beta 2 hat times 1. So, rearranging the terms, we can write the predicted value of the response as beta naught hat plus beta 2 hat plus beta 1 hat x1i. And in contrast, when d equals 0, the response is beta naught hat plus beta 1 hat x1i, and the third term vanishes because we replace d by 0. So here we can see that when we take the difference to read the change in y, what we are left with is the difference in the intercept, which is beta 2, and the slope remaining the same, which is attached to the continuous predictor variable, will give us two parallel regression lines with parallel slopes. So in the following few slides, I will use R and an example data set to explain how we can fit a regression model using a dummy variable and how we can read the output. So here is the problem that we will consider. The data concerns 25 occupational groups and are condensed from data on thousands of individual men. The explanatory variable here are work category and number of cigarettes smoked per day by men in each occupation relative to the number smoked by all men of the same age. The response variable is the standardized mortality ratio for deaths from lung cancer. We will perform a regression analysis to determine the effects of occupation category and smoke index on the outcome cancer index, which is our response variable here. So the very first thing that we do in R is first read the data for each of these variables into R. The first predictor variables that we have is smoke index, and we read the data, the numerical data, into R. Next we read the numerical data of cancer index into R, and finally we have not numerical but qualitative data for occupation that we enter into R. In case we want to use regression with dummy variable in R, then we will have to first define the categorical variable as factor, and that is what we have done here. We redefine actually the variable occupation and define it as factor. Thus, the three factors that we have here are outdoor, office and factory. So now we put all these three variables, smoke index, cancer index and occupation, in a data frame and summarize the data frame we've called cancer. So for each of these variables, we have the minimum, the maximum and the mean for smoke.index and cancer index. So in the above R code, we read the data into R and convert occupation to a factor variable. Then all the variables are put into a data frame. So after we convert occupation to a factor variable, what we are actually doing is converting into a dummy variable, where x, which is the categorical variable, takes value 0 when occupation is working at a factory, takes value 1 when the person is working at an office, and 2 when the person is working outdoors. As you can see, factory here is categorized as 0, so this has been used in the future as the baseline. So next we plot the values of smoke against cancer. So when we have a data set on 2 or more variables and we wish to see the relationship between two variables, first step is to plot the data against each other. So as we have plotted cancer against smoke, we can see a slightly increasing positive relationship, linear relationship between the two variables. So we can go ahead and fit a linear regression model to this data and check the diagnostics to see if the fit was a good one or not. But before we do that, we would like to do some preliminary plots to investigate the relationship between the two variables based on their occupation. So on the next couple of slides, we have the box plots for smoke index and cancer index based on the occupation of the person. So here is the R code that we have used to create the box plot. The first is plotting cancer index, where factory, office and outdoor are the three different work environments. Now as we can see here, the mean of cancer index is high for factory as compared to office. However, the one for outdoor is highest, which somehow makes sense because people who work in the office don't get as much chance to go out and smoke as much as the factory workers. So the cancer index for factory workers is higher. Also, people who work outdoors, they have an even better chance of smoking, so their cancer index is even slightly better than factory. And if we take a look at the box plot of smoke index, that will somewhat reflect the inferences that we had made from the box plot of smoke index for the 3 working environments. Now, after looking at the box plots, we would now like to move on to fitting the regression model. So, here is the R code for fitting a regression model using LM function. Here we have fitted a function, a linear relationship between cancer index and smoke index. Cancer here is the response and smoke index is our predictor variable. So, from the R output, we can see that corresponding to smoke index, the slope intercept is 1.0292 and the intercept is 3. We are also given the corresponding standard error, t value and the p values. So, if we look at the p value corresponding to smoke, we see that at a level of significance alpha equals 0.05, we can compare this p value and we can reject the null hypothesis that smoke is an insignificant predictor for cancer. So, including smoke in the linear regression model completely makes sense. So, next, if we want to obtain the confidence interval for our intercept and slope estimate, then here is the function that I have written. The students can go through each line in detail and look at the functions that have been used here. They are the very basic mathematical functions that we can use in R, and after we use this function, we can then use the R dot out object from the LM function that we had used to fit the regression model before to get the intercept and slope confidence interval at a given level of significance. So, after we run this function for the out object of the LM function used before, we can see that we get the same estimates for intercept and slope, which is corresponding to smoke, and everything else remains the same, the standard error and the p value. In addition to the output that we had received before, we now have the confidence interval for intercept and for slope. So, from the p value, we decide that we reject the null hypothesis that beta 1, which is the regression coefficient corresponding to smoke, is we reject the null hypothesis that beta 1 equals 0, and the confidence interval that we have computed for slope also gives us numbers which are positive, which means the confidence interval does not include 0. So, we had rightly inferred that smoke index is a significant predictor for this model. Now, next, here we have used the LM function to use occupation, which is the categorical variable, to use it as a predictor variable and fit a regression line. The response here is cancer. So, here if you look at the parameter estimates, we have the intercept, which is beta 0, occupation office, which is our beta 1, and occupation outdoor, which is beta 2. Now, if you remember the way we had broken up a model which only contained the dummy variable, and if you remember the categorical variable that we have used for the 3 different working environments, which is 0 for factory, 1 for office and 2 for outdoor. So, the students can see that these estimates are actually the differences of the intercepts that we have obtained from the fitted model. And here again, we have obtained the intercept coefficient confidence interval and the slope confidence interval for the 2 predictors. And finally, here we have fitted a regression model with both the categorical variable and the continuous variable smoke. And here is the output, which contains the estimates, and we have 2 categorical variable estimates which correspond to negative 10.542 and negative 4.589. And here are the corresponding confidence intervals. In this module, I have explained how you can introduce dummy variables into a regression model. The introduction of a dummy variable in the regression model changes the interpretation of the regression coefficients in the model. We have looked at how we can define these intercept and the slope coefficient in case of a regression model when we base our model on dummy variables. And we have also seen how we can use a data set and we can fit a regression model with dummy variables using R.